Good evening, everyone. Today is I'm Bandhuga, Technical Events Coordinator for Civil Engineering Sectional Committee. And today is the 15th session of this lecture series. And today the topic is application of lightweight hybrid construction for multi-story houses and apartments. And we are grateful for Professor Tisan Jayasinghe for conducting this interesting lecture series. And we are receiving many positive feedbacks regarding this lecture series. Thank you very much, sir. And over to you, sir.
Thank you, Bandhuka. And so today, good evening. I hope you all can see the white sheet.
Yes. Good evening. Yes, sir. We can see.
Okay. Thank you. Now, when we talk about lightweight, hybrid multi-story construction. So last time I showed you that this precast slab system that will allow us a thickness of 350 millimeters, 90 millimeters altogether with the screen has the potential to span anything up to 6 meters or more, despite its slab thickness being 90, by using 175 millimeter wide beams, where the depth has to be increased as the span increases. So that's what we learned last time. Then we did a rough cost estimate. And what I showed was the weight is nearly 50%. Cost is sometimes even less than 50%. Okay. So it could be 50% or less. Then what he said was, because we are having this system where we precast the beams. So we cast the beams. It can be precast or cast in situ, depending the lifting capacities available. If you have a tower crane, you can even precast these beams. Then, because we are doing a 45 millimeter thick screed, where all these beams are propped, so we prop them. So there are props during the construction. So the deflection is 0. So when you are removing the props, first we have to remove these. Then gradually we have to remove these from the center outwards. We have to remove these center outwards. If we are removing the prop center inwards, outer to inwards, and finally we remove the middle prop, then we immediately increase the span by 100%. So basically we have a situation, we have many props. So when we are removing the props, it should be center outwards. But if we start removing the props this way, remove the props this way, it's wrong. Why? Because we are going to remove the prop in the middle at once, and that can increase the span by 2 times, adding a shock moment onto the system. So that is wrong. So this is the correct way of removing the props. But the center prop can be removed because slab is not subjected to a heavy load. Then the other important thing is, because we are having this only as 45 millimeters, the other advantage is that we can do it at a control phase so that we can finish it perfectly level, and then we can cut it with, so either the tile bed can directly come on this, and another technique available is tile grout. We add 1:1 sand as well. So rather than using grout directly, we can use sand and grout mix, and that will allow us to maintain a slightly thicker tile bed, so that any unevenness on this surface can be taken into account by the tile bed. So you don't need a leveling screed, because if we are careful, we can do this without the leveling screed. So if you look at today's context, we need these because we are supposed to minimize the number of operations. Although we say labor is cheap in Sri Lanka, still, we have to pay 3,500 rupees per day. We have to spend 3,500 rupees per day for a laborer, and 4,500 to 5,000 rupees per day for a skilled laborer. So these 3,500 for a helper, 4,500 to 5,000 rupees for a skilled laborer. So what you see is that minimizing the number of operations is also an important part of this cost optimization process. So today is the 15th lecture of this series, and today is
20th.
20th, yes, 20th March 2024, and page number 1. Okay. So basically what you see is this. Then we have to see what are the possibilities that are available when we try to apply this technology to apartment buildings and houses, and what are the remaining parts of design that we have to do. So far we have covered most of the concrete related designs, like the design of slab system, design of the composite system, design of individual beams. So all those have been covered in great detail. Now today I'm going to talk more about, okay, so because it's a hybrid system, we are going to have little bit of involvement of the wall. So the concrete block wall or the cement block wall is also making a role. So we have to look at masonry design and also the column design. So we'll look into that aspect a little bit. So the number 2. So if I look at a typical scenario, so let's say we have a house like this. So we have the rooms, this area, like wet kitchen, pantry, and bedroom, and so washroom, whatever. It can be anything that we like. And then we might have, so I'm trying to use the same plan that I used earlier to highlight the issues. And then this might be the living area. And you might have a garage and entrance and bedrooms, washrooms, and so on. So what are the issues? So if you look at this type of system, then how can we optimize? So here, these are living areas, so we might have large openings. So we might need some columns like this, and we might need some columns like this, and we can have some columns like this, and we might also consider having some columns at these locations. I'm just marking, but some of these may not be essential. So if they are not essential, we can drop them later. So these are possibilities only. And these locations, few columns. So why we need columns like that? For example, we need large openings, windows. We might need large doors here. And we might need large windows here. And we might need another large opening connecting the living and garage spaces. And here we might need a big window. So when you consider all these possibilities, what is the best way to arrange the beams and how to optimize? So because we are having some columns here, we can certainly run a main beam here. So I'll use purple for the main beams. So we can run a main beam here. And we can also run a main beam in this selection area. Run a main beam here. Run a main beam. Then we have to see in which direction we run the secondary beams, the beams that will support the slab panels. So if you look at that aspect, what you see is we can run a set of beams like this. And we can run set of beams like this. And we can also run some beams like this. If this area is about 2 meters, you don't need, you can directly support onto the beam. And here also we can run the beam like that. So those are the possibilities, which means we are running the slabs this way. Here also we run the slabs this way. So if you look at the scenario, here you can see these slabs will span this way. So these 4 meters, that is 4 meters. So these half that 2 meters. So we have a beam. So this wall will carry a load. This wall will carry a load, and the load has a width of 2.0 meters. And this beam will carry a load. 50% of this will be transferred this way. 50% will go that way. But that 50% will go on to another concrete beam. And there are concrete columns to take that load. So the concern may be the load that is transferred onto the masonry wall. So we have a masonry wall. The thickness can vary between 150 to 200. Minimum is 150. And generally the maximum width of a block wall is 200. So we have an upper limit of 200. There's a load. So there's a panel supported on the wall directly. Then on that, we are going to build another wall like that. And then we might have another slab. So if you consider that the load from the slabs, the slab thickness is 90 millimeters. So we have 1.35 times 0.09 into 25 plus 1.0 for finishers plus 1.5 times the load. Let's the minimum load specified in Euro code is 1.5 for the houses anywhere in the house. But we'll assume something like 2 just to keep a small margin. So this comes to 0.09 into 25 plus 1, 3.25 into 1.35 plus 3. So 7.38. So let's say approximately equal to 7.5 kilonewtons per meter square. That is the load that will be transferred here. So you can see, so at each floor level, we get 15 kilonewtons per meter transferred onto the wall. So the question is, how many floors we can have this 150 millimeter thick wall supporting before it reaches its capacity? So that is a question that we have to ask. That is a question that we have to ask, right? For that, we have to look at masonry design. So I'm planning to cover a little bit about masonry design aspect. So we have to learn how to deal with Euro Code 6. Euro Code 6 covers masonry design. So we'll have a look at how masonry design part of this hybrid construction can be covered. But before that, we look at how to handle the reinforced concrete design part of the frame, so or the structure. So the reinforced concrete part will be these L-shaped columns and the beams supported by the L-shaped columns. So now when you look at the situation, page number 3. So we have to see where these columns will come. So we have a wall, and the wall goes like that. So when we have a wall like this, we can have two possibilities. The first possibility is, okay, we can have a typical 225 by 225 column. So this is 150 millimeters. And so we try to have this column. But there are many disadvantages. One is, we can see it creates a corner. And plastering this corner is a difficult task. It takes time. It takes labor. It will not take any extra material, but it takes labor. And people find that it is unacceptable to have columns projecting like that. So what is the other option available? Other option is have 300 this way, 300 this way, and have a thickness of 150. So it's a L-shaped column. Now let's do a comparison. So this is 225 by 225. The area is 225 by 225. Here the area is 300 by 150 plus 150 to 150. So let's do the numbers and see which one is bigger. So if you look at the smaller one, Bandhuka, can you tell the answer here?
Yes, 1 minute.
Two 225 by 220.
So,
50,625, is that right? Other one is 300 by 100.
other one is 67,500.
Yeah, 67,500.
500.
Okay. So we have two areas. So you can see this column is even bigger. Although it looks small, it's bigger. So if you look at the type of loads that come onto this column, right? So the loads will primarily come from this side. It goes like this until it meets another column. So these are main beam. So every 2 meters, it will have a beam running in the other direction. So you can see these 2 meters, these 2 meters. So all this load from here to here will be transferred onto this beam. And in this direction, if we have 4 meters, say 5 meters, then the load on this beam will be like this. It will have the load. And so let's assume that this is a large window, and the similar windows are in the upper floors as well. So we can simplify the calculation. So what we get is a load of 7.5 into 2 meters into 5 divided by 2. So we get a load of 7.5 into 2 into 2.5. So we get a load of 37.5. So, and it's a continuous beam. So we can analyze it. And you can see it's not a major load. And then we have to see at which level we can have this beam. Because, you know, we need to have if we have a window, we need to have a lintel as well. So if you look at the level that we need this beam, you will see that we have the building, the opening. Generally, the openings are 2.4 meters tall. And each block has a height of 200. So the main beam can have a height of 2 times the block work. So the beam can have a height of 400. And then at the center, we are getting 37 point. And then we have to decide whether we are going to have the beams in this other direction, like this beam, at which level. So that is something that we have to work out. So if it is 2.4, 2.8, so you find that so 2.4 plus 0.4 plus if the height of the beam system is, let's say, another 0.4. So you'll find the floor-to-floor height is 3.2 meters, not excessive. The floor-to-floor height is 3.2 meters. So these numbers have to be carefully worked out. So you have to decide at which level this beam will be run, and the ideal is we run it at the lintel level, so that automatically this beam will form the lintel. So you don't have to spend money for lintel or anything. The main beam will be the lintel as well. So there's an advantage there as well. So you can see, then if you look at this scenario, then here we get a load of 37.5. Half the load will go this way, half the load will go this way. So you can see from each floor, what you are transferring onto the when you consider self weight of all these beams, might be about 20 kilonewtons. So you can see, we are not transferring a huge load, we are transferring a small load when the rooms are small. And I'm looking at this part of the building, I'm looking at this part of the building where this can be about 5 meters and these are around 4 meters. So that part of the, and you can see, because we are transferring part of the load into this side by having slabs, and also we are having windows one on top of the other, the loads on this beam will not be excessive. So this column is very lightly loaded. So what I want to tell you is, we have a column that is very lightly loaded, but it is having a area bigger than this column. So which means this is good news. Why? Because we have a column supporting a main beam, but it is not excessively loaded. So this says, okay, we can have minimum reinforcement on this column. We can have minimum reinforcement on this column. That's good news, because you know we want to minimize the amount of reinforcement needed in the building. So what is the reason for this? The reason is, part of this load is actually taken by the wall. Part of this load is taken by the wall. That is the reason. So you can see, not only with the slab, even with the frame involved, we are going to get advantage where we need minimum amount of reinforcement. So if you look at this scenario, let's look at the column. So I'm showing you the possibilities. So when you do the actual calculations, we can get the exact numbers. So this has 300. This has 300. This has 150. This has 100. Okay. So let's assume that this is axially loaded. Then without reinforcement, and let's assume that we have been smart and we have been able to get a concrete of 2530 C by using some admixtures and also with proper curing. So if we get 25 megapascal concrete, what is the load carrying capacity of this section? Load carrying capacity is 0.567 FCK times area of concrete. How do you get it? Because when you test a cylinder strength is FCK. So the axial load carrying capacity is 0.85 times FCK. And we have to divide it by the partial factor of safety for material strength 1.5. So 0.85 divided by 1.5 is 0.567. So we can substitute 25 here. And we can substitute the area 67,500 here. And we can see divide, and we can say 10 to the power minus 3. And you will see that this can carry 0.567 into 25 into 67,500, which gives 956 kilonewton capacity. So you can see this column, although looks small, it is not small. It is bigger than typical or the most familiar size of columns. 225 by 225 column is bigger, and it can carry about 956 kilonewton. And its buckling tendency is very low. Why? It's L-shaped, and each direction has a length of 300 millimeters. So the tendency for buckling is very low in this one, because it has a 300 millimeter length in one direction. Although this part is empty, but the buckling tendency is very low. So we can provide 0.2% reinforcement as practiced in the Euro code. So 67,500 into 0.002 is equal to
130.
135. 135 millimeters. But Euro code says when you are providing reinforcement, the minimum size for the vertical bar is 12 millimeters. So you need 12 millimeter bar. We need one bar. So the moment you have bars like that, we can have a link. And we can have another link. That also can be provided 2 bars. So the minimum number of bars that we need in this column is 5 numbers of 12 millimeter, giving 113 into 5. So something like 150 millimeter square is much more than what is given there. Then we can have links at 20 times diameters. 20 into 12 is 240. So we can have links at 225. And Eurocode recommends at the top, at the bottom, 400 millimeters. Reduce this spacing up to 0.6. So 225 minus multiplied by 0.6 gives something like 150. So here we can have 150 center to center. Bottom 400 millimeters, 150 center to center. So you can see we need some links, and unfortunately we don't have any bar size less than 8 millimeters. So this link has to be 8 millimeter. Because Eurocode does not allow MySteel. So it says any reinforcement should be 400 to 600 type. So it does not say that, it doesn't talk about the link. So link also should be the same strength. So because of that reason, the smallest size of the reinforcement available in the market is 8 millimeter. So we have to use 8 millimeter links. 8 millimeter links. But this shows the possibility. That we have a column which actually goes into the wall. But then you might ask, why don't we go for 300 by 150 column? We all know this 150 is not a very safe dimension, because this might have a tendency for buckling. So why we go for L shape is to prevent that tendency for buckling. So the moment you prevent the tendency for buckling, how the column fails? Column fails by crushing of concrete. The moment we prevent the tendency for buckling, the column fails by crushing of concrete. So we ensure that the column fails by crushing of concrete, not by the buckling of the column. So that's why we go for this L shape. Otherwise, you can see this L shape is not a need unless for the buckling tendency of thin columns. So because the column, we deliberately make the column thin because of practical advantages, like not showing the presence of the column at the corner. We are actually going for L shape, right? Which is actually larger than the normal column. We need little extra concrete. But if you look at the system, the main advantage is we run the main beams only in one direction. We run the main beams only in one direction. We run the main beams only in one direction. All the other beams are the beams of the slab system, or else we might have a beam at the lintel level like this, or else we are making use of the wall to carry the vertical loads, or else we are making use of the wall to carry the vertical loads. So because of all these reasons, you can see we can get a significant cost advantage because we are using the minimum size reinforcement, and even if you go for 5-6 stories, still we can go with the minimum size of reinforcement. So that's a huge advantage. That is a huge advantage when you consider the cost of construction. And the other important aspect is, these columns are not obstructing the arrangement of interior, because columns can be made part of the wall system. Columns can be made part of the wall system. Is that clear, Bandukar?
Yes, that is clear, sir.
Right. So now you can see there's no major issue with the columns. There's no major issue with the columns. And the beam, main beam is also not a major issue. But it's most likely that because we are going to have this main beam at the lintel level, we will have to design the main beam as a rectangular beam of 400 deep, 150 width. So we have to design it as a 400 deep, 150 wide beam. So there's no buckling tendency of in any of these members because they are all part of the masonry and concrete system. So then you might ask, okay, so we can see the possibilities for apartments, but I would like to take one step further, explaining the possibilities for apartments. So in an apartment building, we can have large spans like this, where two of them might form, or one of them might form the apartment, or two of them might form the apartment, right? Depending on the size. So this can be about 7 meters. This can be about 8 meters. 7 into 8, maybe 8 multiplied by 7, 56. 56. So this area is about 600 square millimeters. So in an apartment building, what we can do is we can go for large spans like this with the columns at the corners. So this is only a possibility. So you have to think and see how best we can optimize. So we can get the whole apartment, or about 50% of the apartment, onto one panel like this. Then when it comes to apartments, we have a major requirement. What is that requirement? We need washrooms. So we can have walls around the washrooms. And then you can run the panels like this. And we might need an extra column here, because we may have to run additional beams from here, because this can be about 2 meters. So why we prefer masonry for a washroom is, we can, on the masonry wall, we can support the panels. On the masonry wall, we can support the panel, and we can easily have a drop, because the washrooms need a drop of 200, and we can have a drop up to 200 millimeters. Why? Because the height of the block is 200 millimeters. So we can have the panel with a drop of 200 millimeters and fill this up. So this can be 200 and our panel is also can give 90, so this can be 110. So we make up 200 millimeters and then we can run other main beams. The advantage of this is that now if you are going to have any partition wall, it is not a major problem. Why? These beams, now if we want a partition wall, what we have to do is below the partition wall have a lintel or a beam of 200 millimeter depth, and the partition walls can be 100 millimeter. So what happens? This beam will transfer the weight of the partition wall onto this beam and onto this beam. And when you are designing the beam, because we have to design the beam for all these loads, then you will find beam is subjected to a UDL plus a point. So it's a matter of designing the beam, this beam to carry it. So you can see there's a huge possibility that is not available with solid slabs, because solid slabs are not capable of supporting this kind of partition walls without having huge amount of extra reinforcement. Whereas in this system, because we are having beams, we can easily support any kind of partition wall either across the beam or along the beam. So we can have a partition wall here, no problem, because this beam can be designed to carry the weight of the partition wall. So Bandhuka, can you see the advantage of this system for apartment buildings, right?
Yes, sir.
So you can, if you carefully plan the apartment building, this is a need a lot of planning.
Yes, sir.
But you can certainly make sure that the system is very efficient, and you don't have to go for a lot of walls at various locations. You can concentrate the columns at few far apart places, run the main beams, and on that run the apartment, so that all the apartment loads will be transferred to the main columns that you have selected.
So one question, sir. When developing these floor plans, whether the architectural stage, those things should go parallelly, or
So basically you have to work with the architect and make the architect understand that what are the positive side, or what is the positive side of this system, so that architect will adapt to the positive side of it, right? Because this has a lot of positive aspects. Now, one of the biggest problems that we have in the apartment buildings is the partitions are everywhere, and transferring the weight of the partitions to the ground level is not an easy task, right? So whereas in this system, what we need from the partition walls is they being lightweight. If they are lightweight partitions, we can straight away have them on this slab system without having a much cost penalty, right? Is that clear, Bandhuka?
yes, that's clear.
So basically, certainly we have to work with the architect. So basically, because architect decides, so we have to make the architect understand, because what you have to understand, what you have to keep in mind is, now at the moment we have a huge crisis in the construction industry, because nobody wants to invest. So if you want to bring the investment in, we have to think differently, right? We can't think in the traditional way and make things happen, because in the traditional way costs are too high. We have to bring the cost down, but with innovative thinking. So that's the way forward. So what you see is we need some kind of adjustment, and so there are many opportunities available for planning apartment buildings. So we have few undergraduates and postgraduates working on all these aspects of how to plan apartments, what are the rules that the architect should be known, what we have to tell the architect, okay, how to think of the structural requirements and what are the advantages of this system. And also we have to think about how to make use of very lightweight materials like autoclave blocks, aerated autoclave blocks, or lightweight partitioning materials, where the cost advantage will come because they are lightweight. We can make a saving on the reinforcement. So likewise, we have to think differently, right? But when I presented the slabs, what I said was, when we have two 2H8 bars, 2H8 bars with uh, with the beam supporting it, and make it continuous by having continuity reinforcement. This 2H8 at 150 can give a huge capacity. So sometimes you will find these additional beams are not essential. If you have done the construction properly, even the slab system can take it, because when you support a wall on a panel, the weight of the wall is W. Only 40% of W will be carried by this panel. The remaining 30% and 30% will be carried by the adjacent panels. So when you apply a load on a width of 300 millimeters, the actual load will be carried by a width of 900 millimeters. So because of that reason, and also we have 90 millimeters spanning only 2 meters, it gives a huge potential. So if you have any lightweight material, you'll find this lightweight material can be directly supported on the slab without having any concrete elements. So this opens up a new era where we have to think more and more about lightweight materials, lightweight panels or lightweight blocks. So that's where the future lies, because when we go for large spans, this system itself is lightweight, right? And the other advantage of this is, this need not be 150 blocks. If you are going for large apartment buildings, we can actually go for 200 millimeter blocks, which will allow this column to be automatically bigger, like 400 by 200, something like that, giving even a bigger possibility, provided the architects are willing to take up the challenge of going for open architecture, where the lighting and all those requirements can be satisfied, and also the washrooms can be located one on top of the other. So that the moment you satisfy those conditions, we have been looking at these possibilities. What he thought was, okay, there's a great possibility to plan the buildings using this system. So that's what we actually found. So what I say is, we like many of you thinking about these possibilities, because this may be the future. The reason is we can reach a cost saving of around 50%. Is that clear, Bandhuka?
Yes, that's clear, sir.
Right. So basically, why I present this is, we like many of you thinking positively and thinking about it,
Yes.
the advantages that this can offer, and also explaining these structural systems to architects, so that they will also will start thinking in the same lines, and they will come up with feasible solutions that
Yes.
will finally give us huge cost advantages, and the industry will find investing, or the general public will find investing in buildings is a possibility again. At the moment, they consider it's not a possibility. But the moment they find the costs are lower, they will find investing in the industry is a possibility. So what I feel is this lightweight hybrid multi-story construction has a huge potential to revive the industry. Right? Is that clear, Vanduka?
Yes, yes, sir. That's correct, sir. Yes.
Yeah. Then we also have to think about the commercial buildings, where the situation is different, where we will have large buildings, large spans, and then so things like that. This is the last span. So in this area, core, and these areas being slabs, main beams. So the possibilities, all these can be easily converted to these thin slabs. So these are the thin slabs. Although the spans are large, the thin slabs can easily span any length, because one is they are lightweight. Secondly, they are supported by beams. So there are two possibilities. So basically, you can see the applications can be there for even tall and super tall buildings, irrespective of the application, especially in commercial buildings. There's a huge possibility. And what you find is, this is not something new. If you look at textbooks, you can find things like rib slabs. But what is new is, now these rib slabs did not have shear reinforcement, usually. Whereas the beam system we are designing has shear reinforcement. So it has shear reinforcement. So this has a huge strength, because we are not relying on the strength of concrete to carry shear. Whereas if you look at most of these rib slab systems and so on, we rely a lot on the ability of concrete to carry shear. Whereas in this system, we are not relying on the ability of concrete to carry shear. We are providing shear links. So we are providing shear links in a lightweight system. So that's why it can span over long spans, like 6 meters, 8 meters, all are possibilities. Because 8 meter is a big span. But because we have a lightweight system, the slab thickness is only 90 millimeters, and each beam supports a load of only 2 meters, 2 meter wide strip. You'll find, so all these strips are only 2 meter wide. So columns carry, beams carry only that load. So you find the system works very well. because it has no restriction on the spans. So that's how it can become a viable solution even for tall buildings. And the other advantage of tall buildings is all these can be precast. Sometimes these beams can be even pre-stressed concrete. These precast beams can be even pre-stressed concrete, because we really have no need for it to be reinforced concrete. So these long beams can be pre-stressed concrete. The advantage is all the tall buildings will have a tower crane. So the moment there's a tower crane, lifting the beams, placing them, all can be done with the tower crane. So there's a huge cost saving, because lifting these is a very tedious affair when you try to do things manually. Whereas if you have a tall building, most of the building can be precast elsewhere and fitted at the site with necessary continuity reinforcement to make the super tall building to be super light while having the robustness. So that's the future possibilities. Is that clear, Bandhuka?
Yes, that is clear, sir.
Okay. So these are all possibilities. So there's a huge potential for us to do more and more studies, case studies, practical applications. But we have to be a little bold and do it, because otherwise it will be another good solution that was limited to research and development. So we like it to be taken to a new stage. So that's where, so in tall buildings, you will not have many restrictions. The masonry will not be carrying the job. It will be concrete, but this allows us to bring in pre-stressed concrete, PT, into the building by precasting the beams. And not only the beams, even the slabs can be precast with pre-stressed concrete. So all these are possibilities, and especially in large buildings, there's a possibility to precast the whole building, most of the building, except the main columns and beams elsewhere, and fitted at the site. Because you all know, concrete slab is a major task even in commercial buildings, because it needs a lot of attention, lot of work at the site, and that all can be reduced if we develop these systems more, because this has the huge potential, especially because of this shear link. Because most of these restriction on the other systems had been that they have tried their best not to have shear links because they are cumbersome. But in this particular system, because we are going for precast slabs of 2 meters, we have only few beams, and those can be precast or in situ cast, depending on the requirement. And the main aim is minimize reinforcement. And the other aim is remove any concrete that is not doing anything useful. Remove as much concrete as possible if it is not doing anything useful. So that's where the PT also comes in, because in the PT section, the whole section is effective. So PT also has, pre-stressed concrete also has a huge potential in this system, where the PT beams have to be cast with links. That is not a major problem. You can do the precasting operation with shear links. That's not a major hurdle. So that can be done. Okay, Bandhuka?
Okay, sir.
Right. Now let's look at masonry design. So I will use a note. I'll share the screen now.
Okay, sir.
Right, I'll share the screen. So I'm sharing. So I'm sharing
Okay.
our undergraduate note
Okay, we can see, sir.
where we teach masonry walls, right? So you are all familiar with masonry, so I don't have to explain a lot about masonry. But I'm going to talk about the strength of masonry because the first thing is to know what is the strength of masonry. So there are so many different types of masonry available like this. You can do masonry with insulation, all kinds of possibilities are there. And then so you can see for masonry also, we use the same partial factors of safety 1.35 GK plus 1.5 QK. And then in Euro code, we all know there are 5.0, 5.1 and 5.2 factors. And for wind loads, 5.0 is 0.5. And for live loads, 5.0 is 0.7. And that is the exact values that we use in reinforced concrete design. So when you have dead load, live load, and wind load, we have a load case 1.35 GK plus 1.5 QK plus 0.5 times, here you get 0.5 times 1.5 WK. So it gives 1.35 GK plus 1.5 QK plus 0.75 WK. Then where dead load, imposed load is dominating. Then we can have the wind load dominating. Then in that case, 1.35 GK plus 0.7 times 1.5 times GK plus 1.5 times WK. So then in that case, we get 1.35 times GK plus 1.05 times QK plus 1.5 times WK. So that's the same thing that we do in masonry and concrete. No difference at all. Same thing. And then when you look at pattern loading, the same pattern loading. Pattern loading is the same way as in concrete. And then when you are looking at the different combinations of lateral loading, you can see 1.35, 1.5, 0.75, 1.35, 1.05, 1.5. Likewise, the same scenario as in concrete. And then we'll skip that because that is not relevant to us now. Right. Then we can have mason units. And there are so many different types of mason units. And so there are hollow units. So here we are promoting hollow units made out of concrete aggregate units, having the opening area between 25 to 50%. So that's the type of blocks that we manufacture in Sri Lanka. Because we are hollow blocks, but they have a certain wall thickness. So when you look at the total gross area of the volume, you'll find it's between 25 to 50%. But you can actually measure it and see which category it is, but generally it is in this category. So what you have to keep in mind is we are looking at a group of masonries which is 2A. Then it says, okay, we have to use certain mortar. And generally we use M2 mortar or M4 mortar or M6 mortar or M12 mortar. But in Sri Lanka, generally we use M4 mortar, which is 1:5 or 1:6 cement sand mortar without air entrainment. So when you use 1:5 mortar, generally we can get a strength of 4 megapascal. So that's why we call it M4 mortar. The expected strength is 4 megapascal. 4 megapascal, right? So basically M4 means the number following the M is the compressive strength for the class at 28 days in newtons per meter square. So when you say M4 mortar, we are looking at a mortar which gives a strength of 4 newtons per millimeter squared or 4 megapascal. And to get that, we have to use 1:5 cement sand mix. But the important thing is the cement sand mix should not be mixed in the morning and used in the afternoon. So generally within 2 hours of mixing, the mortar should be used. So we should not mix too much mortar. We should mix the mortar in small quantities, sufficient, so that we can use the mortar once mixed. We should not keep the mortar without being used too long. So otherwise what we do is they keep it long and it sets, then they break it again and then mix with water and use it. So it's not a good practice. So we should make sure that the mortar is mixed in small quantities and used rather than mixing a huge amount of mortar and using over the day. And then now the most important thing is not the compressive strength of masonry unit, but the compressive strength of the wall. So if you look at the compressive strength of the wall, the characteristic strength Fk is given by K times Fb to the alpha, Fm to the beta. So Fb means the compressive strength of the block. Fm means the compressive strength of the mortar. So you can see this Euro code has been very good because when we test the individual block, when we know the type of mortar that we are using, straight away we can find the characteristic strength of mason. Characteristic strength of mason, right? So otherwise, even in the British code earlier, we did not have that kind of data, that kind of tables. But in the Euro code, it's very good. So straight away, we know, okay, we know the type of block, we know the type of mortar, and there's a K factor. So it's a matter of finding the K factor. Is that clear, Bandhuka?
Yes, that is clear, sir.
Yeah, that's a huge advantage because masonry code is not looked by many, but this is a very good code because it helps us to do the masonry design with a limited amount of testing on the type of unit that we are using. Then the most important parameter is K. So if you look at the K parameter, so aggregate concrete, can you remember I said it's group 2, even group 1, all these are around 0.5 value. And general purpose mortar. So we have a situation where Fk is K times Fb to the power alpha and Fm to the power beta. Then you will find when you use general purpose motor of 10 millimeter, 10 to 12 millimeter, for general purpose motor, alpha is 0.7, beta is 0.3. Alpha is 0.7, beta is 0.3. So it's a very useful value, right? So if I look at an example, alpha is 0.7, beta is 0.3. Right? So that's what you get. And K is 0.52. And Fm is, because we use M4 motor, 4 newtons per millimeter square. Very easy. Right? And so what happens? Fk is 0.52, and let's say we are using 5 megapascal units to the power 0.7 multiplied by 4 to the power 0.3. So what is the strength? Strength is strength of masonry. Characteristic strength of masonry is 0.52 multiplied by 5 to the power 0.7, which is 3.08. 4 to the power 0.3, 1.51 into 0.52. So this comes to 0.52 multiplied by 3.08 multiplied by 1.51, 2.42 newtons per millimeter. So if you buy good high quality cheap concrete based blocks, hollow blocks of 5 megapascal strength, at whatever the age you are using it, then the characteristic strength is 2.4. But masonry, when you try to use it as a material, we have to look at it in this context. And that is, it can buckle, right? Because it's a slender wall, 150 or 200. Not a thick wall, it's a slender wall. So it has a tendency for buckling. So we have to allow for that. Then we might not load it axially. We might have an eccentricity when you apply the loads. So you have to take that into account. So we'll have a capacity reduction factor. We'll have a capacity reduction factor. Yeah, look at the capacity reduction. And when you are using characteristic strength, we have to have a factor of safety, gamma m. We have to have a factor of safety on the material strength. Right? So I'll share the screen. So what are the material strengths? When the state of indirect or flexural compression, unfriendly masonry may be units of category 1 or category 2. The factor of safety can be 2.6 or 3. And let's see what is A and B. A means a special control. So under A, we are talking about special quality control. And B means the normal quality control. So it's better to go with B. So you will get gamma M of 3. Gamma M of 3. Gamma M of 3. So, and then let's assume that the capacity reduction factor phi is 0.7. Then what is the final stress we can have? The final stress is characteristic strength divided by gamma M 3 multiplied by the capacity reduction factor 0.7. So you will find the stress that we can have on masonry is now limited to 2.42 multiplied by 0.7 divided by 3 and it's limited to 0.564 newtons per millimeter square. So you can see, so we have a strength of 2.42 as a characteristic strength. It has to be divided by the gamma M value. Even in concrete, we divide the strength by 1.5 factor of safety, gamma M. And because there's a capacity reduction factor, we have to multiply it by 7. Now you find the maximum stress we can have is 0.564. And let's see what happens. Now, can you remember earlier I said at each floor level we get 15 kilonewtons per meter because it supports a panel. And the remaining part of the masonry is self-weight. And if you consider a height of 3 meters and a width of 150 millimeters, a density of 12 kilonewtons per meter cubed because it's a hollow material. Now you can see why I prefer hollow materials because it has a lower density. So each wall will give a load of 0.15 into 3 into 12. So it gives 0.15 into 3 into 12. So it gives 5.4
Yes.
kilonewtons per meter. Is that right, Babu?
Yes, sir. 5.4.
Right. So you can see, so each floor we can say 15 plus 5.4, let's say approximately equal 21 kilonewtons per meter. So if you convert it, you divide it by the width, 21 divided by 0.15 kilonewtons per meter square. The value is 21 divided by 0.15, 140 kilonewtons per meter square, or 0.14 newtons per millimeter square. So 0.56 divided by 0.14. What is the answer? 4. So that means we can have 4 floors where masonry supports part of the slab load. So we have the ground floor, we have a slab, we have another floor, we have a slab, we have another floor, we have a slab, we have another floor, we'll have a slab. That's possible. So you can see, even with 150 blocks of 5 newtons per meter squared strength, possible to go up to 4 floors. And if you have a reputed manufacturer, what they say is, you specify the strength we supply. Why? Because what they have to do is, because this is concrete based material, you ask for 5, they make sure they cure it, keep it moist, and they cover it with polythene, and then the curing will continue. What they have to increase is the cement content. Sand, aggregate, everything will remain the same. So the cost of the block will rise slightly, but you can increase from 5 to 7 or 5 to 8. So which shows a huge potential in this system, where you can have either 150 millimeter blocks or even 200 millimeter thick blocks. And you can see, when you combine the lightweight slab system, with the lightweight blocks, the opportunities are huge. Is that clear, Bandukar?
Yes, sir. That is clear.
So next day we can discuss more about masonry design, how to think about the openings, the stress concentrations, and also how to calculate the capacity reduction factor accurately. So all those things we'll have a look, so that
Okay,
you can handle this combined design. It's not only RC design. This involves
yes,
RC design, this involves masonry design. So it's a combined effort that we need,
yes, sir.
right? So with that,
Okay, sir.
we can conclude today's lecture. If there
Yes, sir.
are
Yes. Yeah, there
questions in
are
the chat,
3 questions.
yeah. What
One
are the
is,
questions?
is it possible to use L shape for the column footing?
L shape for the column footing. Column footing also to be L shaped. That is not a major problem, major challenge, but we don't have a specific reason to do that, because why we use L shape is we want to embed the column into the wall, but at the foundation level we don't have any restriction as such. So you would be better off using a rectangular footing, right?
Okay, sir.
Right.
And the other question is, in solid slab, similar, shall we consider as strip slab and design additional rebars for this partition wall loading?
Yeah, you can do that, because if you look at Hillsborough strip method, that covers that aspect, but that is not the exact problem. Problem is you need a lot of reinforcement. Whereas in this case, we increase the reinforcement in the beam, which is a much better element structurally than a slab to carry heavy loads. Now, slab is actually a ideal element to carry light loads. Beam is a ideal element to carry heavy loads. So, in the normal solid slab system, when we try to carry concentrated loads, we are using a slab which is not meant for heavy loads to carry heavy loads. To allow for that, you can use Hillsborough heat strip method and design the reinforcement. There is no question. But you will end up with a huge amount of reinforcement. Like you need 12 millimeter bars at 100 spacing over a width of 0.6 or 0.8 meters. Huge number of bars. Whereas in this one, you might increase a 12 millimeter bar. The whole increase may be 112 millimeter bar in the beam. So that's the difference. So that's why I said this system is more efficient because we are using beams with shear links. We can make it very robust. Whereas that opportunity is not available with solid slabs because the moment we try to carry heavy loads on solid slabs, the solid slab thickness has to be increased. The moment we increase the solid slab thickness, only at one location we have to carry the heavy load, but we are increasing the slab thickness everywhere. Is that clear, Bandhuka?
Yes, sir. That is clear.
Because we are increasing everywhere. We are increasing. Why? Because we have to carry heavy loads. Whereas in this one, it's a concentrate. I mean, we are just adjusting something in the beam, or sometimes we can specifically carve the slab with 3 numbers of 8 millimeter bars instead of 2 numbers of 8. So something what we do is very local. So that's the advantage of this. I hope I have.
Yes, sir. That is clear.
The question.
Yes,
yeah.
And the last question is how about the T sections columns in the middle, columns in the building, and how can we collaborate the L sections and T sections of columns in flat slabs?
Yeah, so basically L-shaped column footing, column, yeah, so are possible to use L-shape for column? That is not the question.
No,
What is
sir.
the
Discussion is at the top. How about
our T section columns in the middle columns in the building and how to collaborate? Okay, that's not in the case of flat slabs. Okay, now if you are going for flat slabs, it's a matter of shear. So basically, in the flat slabs, the most critical aspect is the shear, not the flexion. So how are you going to carry it? Take account of shear, the punchy shear around the column. So if you are going to make the column size bigger, then you have a particular advantage. And if you look at the handbooks, there are methods of how to handle the punchy shear around columns of odd shape, not the rectangular shape. So those guidelines are given in the handbooks. So you can handle it, but now why flat slabs are discouraged in Sri Lanka is the whole concept behind flat slab is you save the labor, not the material. Flat slabs are thick. They need a lot of concrete and steel because they are inefficient in transferring the loads onto the columns. But they are very efficient when it comes to construction. So that is the philosophy that we have to do away in Sri Lanka, because in Sri Lanka materials are very expensive, labor is cheaper. So there's no point in trying to go for high material, low labor type of construction. We have to always go for low material, though the labor can be slightly higher, not excessive, but slightly higher. So that's the philosophy we have to follow. Okay, Bandhuka.
Okay, there's one last question, sir. When we provide main beam in one direction, what about the sway in other direction for more stories?
Oh, no, actually, that is something that you have to handle by, for example, if it is a house, there's no problem because you have, because there will be partition walls in the building, in a apartment building. But in a case of commercial building, the core is there to handle that part of the problem. The sway part, we can handle with the core of the building, right? So these are the places, slabs that we use for to occupy or rent. So those areas can be as light as possible. Whereas to resist the lateral loads in commercial buildings, we can go for the core. We can rely on the core to handle it because we can have concrete walls there. Whereas in the apartment buildings, we can do the planning in such a way that, in both directions, we have solid walls so that the sway of the building can be taken by the mason. So that's the way we have to look at it. Is that right?
Yes.
Now,
Yes,
even if you look at this plan, now here you can see there are masonry walls here. So there is no way that it can sway, but here also you might have some masonry walls in fields. Because
Okay.
that is a space that we separate. Though we run the main beam in that direction, we can have masonry walls, right? So
Okay.
these, generally the separation. So you have to actually carefully plan it so that there will be some masonry walls in both directions. And masonry walls, the advantage of here is the masonry walls are loaded. The loaded masonry walls are extremely good in carrying lateral loads. If you have a masonry wall which is not loaded, then it can, slip and fail. Whereas when the masonry is loaded vertically, they are extremely good in carrying lateral loads. So we have a particular advantage in this system because we are loading the masonry wall. So the structure becomes super robust, very robust. Is that clear, Bandhuka?
Yes, that's very clear, sir. I think that's all the questions.
Okay, thank you very
Okay,
much.
thank you, sir. And
Thank you.
as I mentioned, we are having a downfall in the construction industry. So I think this lecture series has eye-opener for those who are interested in cost-effective approaches and I think most of the participants will bring this message to the construction industry as well. And thank you very much, sir, providing your expertise and knowledge on this. And also, I would like to thank the Chairman, Civil Engineers Sectional Committee, Engineer Mangala Silva, for continuing this lecture series for this year. Thank you very much. And also, I would like to thank the ISS Secretariat, Publicity Department, and IT's Division for their hosting arrangements. And also, I would like to thank all the participants and for their questions and for continuously participating in this lecture series. That is also very important for the success of this lecture series. Thank you very much. And good night to everyone. Thank you, sir. Thank you very much.
Okay, thank you very much. Thank you. Thank you.